All right, today we're going to be talking about rotational kinematics. Everyone remembers Unit 1, kinematics, what we now call translational kinematics, because we are now differentiating between translational motion, or an object's movement through space, with rotational motion. It's rotation around an axis of rotation. So let's take a moment to do a quick reminder on what we talked about last class, which is that we have relationships between these different variables that show up in rotational motion and translational motion. So we have analogous variables between the two different types of motion, and each set of variables is related through a radius. So when we thought about position for translational motion, we now, in rotational motion, think about the position of an object as its angle from the center of its rotation. And we can relate those two variables, the translational position or the rotational angle, through these two equations right here. And then we can do the same thing with translational velocity and angular velocity, which they have a very similar relationship between those two translational rotational variables. And finally, we've got translational acceleration and angular acceleration, and we can also relate them through radius to one another. So, using those relationships between our translational variables and our angular or rotational variables, we can now take our kinematics equations that we use for translational motion, and we can make new equations from them that we can use for rotational motion. So we're going to walk through a quick example of one of those equations, but you can do this with any of the big four motion equations we talked about back in Unit 1, our translational kinematics unit. So let's take a look at our equation that relates final velocity to initial velocity, acceleration, and time. So we've got our final translational velocity will equal our initial translational velocity plus our acceleration times time. And if we take those translational variables and relate them with our rotational variables through radius, we can first relate our final velocity to our final translational velocity to our final angular velocity. And remember that translational velocity equals angular velocity times radius. So we can plug in for our velocity, for our translational velocity, angular velocity times radius. And we can do that for final velocity, and we can also do that for our initial velocity. And then we can do the same thing for our translational acceleration, because our translational acceleration equals alpha, or our rotational or angular acceleration times the radius. And so we can plug in for our translational acceleration, angular acceleration times radius. And obviously, time will not be a different variable whether we're moving, will be the same variable whether we're moving translationally or rotationally. And finally, we know that there are radius. The radius is in every single one of these terms, so we can get rid of radius. We divide each side of the equation by radius, and we end up with our final angular velocity equals our initial angular velocity plus our angular acceleration times time. This is a little bit of a mouthful to say now that we're saying angular before each one of our variables, but you'll notice that this looks the exact same as our translational equivalent, just we've replaced our translational variables with our rotational variables. And we can do that for every single one of our UAM equations, every single one of our uniformly accelerated motion equations. And now, rather than uniformly accelerated motion, we're thinking about uniformly angularly accelerated motion, or uniformly accelerated motion in a rotational capacity. And just remember that just like our translational kinematics equations, all of these equations require that our acceleration is constant and uniform throughout time. And obviously now this time we're thinking about our rotational acceleration being constant and uniform through time. But you'll notice that all four of our equations look the exact same as our UAM equations we talked about in Unit 1. Just now we've replaced our translational variables with our rotational variables. So let's take a look at a few example problems, shall we? So let's first think about some trains. All right. So large freight trains accelerate very slowly. Suppose one such train accelerates from rest, giving its 0.350 meter radius wheels an angular acceleration of 0.250 radians per second squared. After the wheels have made 200 revolutions, and if we assume there's been no slippage, so the rotation of the wheels has been constantly moving through the track, then we can figure out a few things. So let's first think about how distance or displacement relates to the information that we do know, right? And so since we're thinking about how far the train has moved, we're thinking about our translational motion of the train. So that means our displacement or our delta x. And we know that we can relate our translational distance to our rotational distance or our rotation angle by multiplying it by radius. So if we think about what information we know, we have our rotation angle or our data theta. It was that we have moved 200 revolutions. We have our tires have spun 200 times. And remember that every one revolution is equal to 2 pi radians. So if we convert that to radians, that gives us 1,257 radians. And again, radians aren't really a unit, but I will write them begrudgingly, even though they're not a unit. And we also know that our radius of the wheels is 0.350 meters. And so if we want to solve for the displacement of our train, we can take the number of rotations of those wheels times our radius, and we can figure out how far our train has moved over that period of time. So take 1,257 radians, which is again our rotation angle, times 0.350 meters. And that gives us a displacement of 440 meters. Okay, so we didn't really use any kinematics just yet in the last question, right? We just converted from our rotational variable, rotation angle, to our translational variable, distance or displacement. So let's next think about what's the final angular velocity of our wheels. And to figure this out, we do need to think about our kinematics equations, right? So we're trying to figure out what our final angular velocity is, or omega f. And that should be in radians per second, right? Or just inverse seconds. And we know a few things about the train's motion so far, right? The first of all is that our initial velocity was 0 because we started from rest. So our initial angular velocity is 0 radians per second. We also know that we had an angular acceleration, or an alpha, of 0.250 radians per second squared. And finally, we know that our delta theta, or our rotation angle, was 200 revolutions. And again, that was 1,257 radians. Okay, so obviously we can look up what rotational kinematics equation will fit here. Which one will use these four variables: final angular velocity, initial angular velocity, angular acceleration, and our rotation angle. But let's first think about, because we probably know this off the top of our heads, which of our translational kinematics, or our old big four equations, would relate for us final velocity, initial velocity, acceleration, and delta x. And if you think back, you might recall that we had an equation that related our final velocity to our initial velocity by taking final velocity squared equals initial velocity squared plus 2 times a times delta x. And again, it's very easy to go from our kinematics or translational kinematics equations to our rotational kinematics equations, because all we have to do is just substitute out the variables, the rotational variables from our translational variables, right? So I can rewrite this now just putting angular velocity in for our translational velocity, and angular acceleration in for our translational acceleration, and finally our rotation angle in for our delta x. So now that we've got a working kinematics equation, let's first get rid of anything that's zero. So remember, our initial angular velocity is zero, so we could just get rid of that term, right? Which means that our final angular velocity squared equals 2 times alpha times delta theta. And finally, if we just want our final angular velocity, then we're going to take the square root of 2 times alpha times the change in theta, right? And if we plug those numbers in, that's 2 times our angular acceleration, which is 0.250. Again, I'm going to leave the radians per second squared off just because remember radians aren't really a unit. And then finally we've got our change in theta or our rotation angle, and that's 1257 again in radians, but radians aren't really units, so we don't need to worry about that. And so if we take it, we plug that into the calculator, we end up with about 25. And again, that was inverse seconds squared. We took the square root of that. So that is inverse seconds. So we could say 1 over seconds or 25 inverse seconds. Or if we wanted to, we could include radians in there. So it's radians per second. Again, radians are in units. Cool. Okay, so we now, as long as we can find a rotational kinematics equation, and again, just like back in Unit 1, if we have three of our variables known, then we should be able to find the other two of our five kinematics variables. Obviously, now we're dealing with our rotational kinematics variables rather than our translational kinematics variables. And then finally, if we wanted to convert this angular velocity into a linear velocity, again, we know the relationship between linear velocity and angular velocity. And it's just if we take our angular velocity times the radius of the circle around which that object is going, then we get our translational velocity. If we want to be specific for our units, we could label both of these as final. Great. And then we can find our final our final translational velocity by multiplying that angular velocity, or 25 radians per second, times the radius, which was 0.350 meters. And that should give us about 8.8 meters per second. So we can use our rotational kinematics to figure out our rotational variables throughout an object's motion, as long as we know, again, at least three of those rotational kinematics variables, three of the five, we should be able to figure out the other two. And given that we know the relationship between rotational motion and translational motion, then as long as we know the radius around which that object is going, the circle around which the radius of the circle around which it is going, then we can relate that that rotational motion to its translational motion. Okay, let's take a look at another example problem. So now we've got a fishing rod. So the fishing reel and a fishing rod is going to obviously go through to rotational motion as it allows the line to come out. And what's neat about this is that as the line comes out, the amount of line that we get obviously is going to be related to the number of rotations that the reel goes through, right? So we'll see an actual unspooling, and that unspooling, the rotational motion, will give us the distance and the speed of the line coming out. So a deep sea fisherman hooks a big fish that swims away from the boat, pulling the fishing line from his fishing reel. The whole system is initially at rest, and the fishing line unwinds from the reel at a radius of 4.50 centimeters from its axis of rotation. The reel is given an angular acceleration of 110 radians per second squared for 2 seconds. So let's find the final angular velocity of the reel. And again, what we need to do is we need to relate what we know and what we don't know, right? So let's find out our knowns. So we know that the radius of the wheel is 4.50 centimeters. And we know that the angular acceleration is 110 radians per second squared. We know that the amount of time that passed during this interval of time is 2 seconds. And we need to know at least one. So we have three variables right now, right? But our radius is not actually one of our kinematics variables because that doesn't show up in our four kinematics equations, right? So we need one more of our kinematics equations. Our kinematics variables, those being our rotation angle, right? Delta theta. So we need delta theta, or our final angular velocity, our initial angular velocity, our angular acceleration, and our time are our five rotational kinematics variables. So you've only got two of them so far. We need to find a third one. And the third one is that our system starts at rest. So our initial angular velocity was 0 radians per second. So we've got three variables and we are trying to find a final angular velocity, which, given those four variables that we have or want, we have an equation that relates the three of them. And that equation is that our final angular velocity equals our initial angular velocity plus our angular acceleration times time. And since this equation is already solved for final angular velocity, we don't need to manipulate the equation at all. But let's get rid of any terms that are already that we know to be zero, which our initial angular velocity is 0. So let's get rid of that. So this just says that our final angular velocity will equal our angular acceleration times time. And so we take our angular acceleration, 110 radians per second squared, times the amount of time that that the line is spooling for, which is 2 seconds, and that would give us 220 radians per second would be our final angular velocity, right? One of our seconds would cancel out. One of our seconds would cancel out at the bottom of radians per second squared with the seconds of the time they're multiplying by. Great. All right, next up, let's find the linear speed that the fishing line is leaving the reel at that point in time after 2 seconds had elapsed. And since we know that our final angular velocity is 220 radians per second, so our final angular velocity is 220 radians per second. And in order to relate that to our velocity, we know that our angular velocity times our radius gets us our translational velocity, and our radius is 4.50 centimeters. So if we take our final angular velocity, 220 radians per second, multiply that times our radius of the spool, and we end up with 990 centimeters per second is our final velocity of that line. So how quickly that line is coming out and how quickly the hook on the end of that line will be moving by the end of that 2 second interval. Okay, so next up, let's find how many revolutions the reel made in those 2 seconds, that 2 second time interval. So just as a quick recap, we have four of our kinematics variables solved for, and so that means we should be able to find our final variable, which is just rotation angle, right, or delta theta. So that's how many revolutions does the reel make in 2 seconds. All right, so we have four variables, but remember that our final angular velocity we found from our first question. So let's just use the initial three that we were given. All right. If we use those initial three, and again we try to find our delta theta, then the equation that relates those four variables would be that our delta theta, or rotation angle, equals our initial velocity times time plus 1/2 times our angular acceleration times time squared. And if we get rid of any terms that are 0, we know that our initial velocity was 0, and so this whole term will end up being 0, right? So that gives us an equation that says our rotation angle equals 1/2 times our angular acceleration times t squared. So that means 1/2 times 110 radians per second squared times our time, which is 2.00 seconds. and then we will square that. And if we look at our variables, we know that our seconds are going to be squared, and we have seconds squared on the bottom on the denominator, and so we'll end up with just radians in the end, right? So 1/2 times 2 times 2, so we should end up with 220 delta theta radians. But the answer here was given in revolutions, so let's think about how many revolutions that is. And remember that every one revolution is going to be 2 pi radians, right? Because when we go around the circle one full time, you go around a circle 360 degrees, or 2 pi radians. If you did 220 radians divided by 2 pi radians per revolution, then we should end up with 35 revolutions. So I'm going to go change that answer key. This should be 35 revolutions. So in that 2-second time interval, the reel will have spun 35 times. All right, next, let's think about how many meters of fishing line came off the reel during that 2-second time interval. So we know that the reel spun around 35 times, and we also know that the radius of that wheel is 4.50 centimeters. So we can think in terms of revolutions, but actually something that's handier is thinking in terms of radians, because with that unit, we can find our displacement, right? So displacement is our delta theta, or our change in rotation angle, times our radius, right? And since radians are unitless, if we multiply that times the centimeters of our radians, then we should end up with centimeters as our answer. So we have got 220 radians times a radius of 4.50 centimeters. Then we end up with 990 centimeters, or if we convert that to meters, 9.9 meters would be the displacement. And that is how much line came off of our reel as it spun that 220 times, or 220 radians, or 35 times for that 2-second time interval. All right, and finally, let's think about after that 2-second time interval, if a brake is applied to the line and that brake is negative 300 radians per second squared in angular acceleration, then how long will it take the reel to stop? So we're considering here is that we have a brake or an angular acceleration of negative 300 radians per second squared. We know that we're going to stop at 0, so our final angular velocity during this time interval will be 0 radians per second. And in this time interval, we actually started at the final velocity for our 2-second time interval, right? So at this point, our initial angular velocity was 220 radians per second, right? So we've got 3 variables there, and we want to know how long. So we're looking to figure out what our time was. And with those 4 variables, we can use our rotational kinematics equation that tells us that our final angular velocity equals our initial angular velocity plus our angular acceleration times time. And if we quickly take a look, we know that our final angular velocity is 0, so that term goes away, leaving us with just initial angular velocity. 0 equals our initial angular velocity plus our angular acceleration times time. So let's solve for time. And what we first want to do is get rid of anything that's adding, subtracting the term with time in it, right? And if we subtract initial angular velocity from one side, we want to do it from the other side. And so we end up with our angular acceleration times time equals the negative of our initial angular velocity. And then finally, we will divide each side by angular acceleration to leave time by itself, now over on the left, equals our initial angular velocity divided by our angular acceleration. And when we plug in numbers over there, the negative of our initial angular velocity, which is 220 radians per second, divided by our angular acceleration, which is negative itself, negative radians per second, negative 300 radians per second squared. And we will end up with radians per second. Our radians cancel out. Again, they're not a unit anyway. And then one of our seconds cancels out with one of the seconds squared in the denominator. And those in the denominator come up to the top. So we end up with seconds in the end. And if we divide 220 divided by 300, we end up with 0.73 seconds. All right, we have one final example, a roundabout example. So we got a child sitting on a playground roundabout while her older brother spins it around. The roundabout has a radius of 1.5 meters and is rotating at 6 revolutions per minute. So we can think about what is the total distance traveled by the child in 2 minutes, and what is their displacement during this time. And I will leave you to figure that out. The answers are provided on this slide. And then once you feel comfortable with those with these rotational kinematics equations, we can put all this into practice with a problem set. So please use this to practice. Thank you for learning about rotational kinematics.